Um, well, I want to thank the IRWP for having me, and I'd really like to thank the other presenters. It's been a fascinating day and a half. I think going at the end, you recognize a lot of people thinking a lot of the some of the from the same perspective, and so you may hear some repetition. I will definitely give them credit, but I'm going to shamelessly steal the mini wheats and the Cheerios example from Brenda and Andy. And I just wanted to say before I dig into some of this that as someone who works primarily in the Mid-Atlantic and Northeast region, I recognize the sort of differences that happen on the landscape, and certainly the differences in funding and policy and regulatory structures we see in our different states. So I just want to be cognizant about that and a bit humble about it, and feel free to ask any questions if something I say seems very Chesapeake centric or Pennsylvania centric. A few things just to introduce you a bit to Stroud and the work we do. So we're a nonprofit research center. We were founded in 1967 with a very clear, simple goal to advance the knowledge and stewardship of freshwater systems. We were founded, if you remember back to that time, I think Seth Brown mentioned yesterday that was the window of time where the Clean Water Act was just getting spooled up, and the Cuyahoga River was on fire. We were in an era of really significant point source problems. And as the folks at the Academy of Natural Sciences in Philadelphia were beginning to be asked to help resolve some of these questions about rivers and water quality, they recognized that one of their most significant impediments was a lack of understanding about how freshwater systems worked, and what a healthy freshwater system looked like and why. And so they cobbled together some funding, working with the Stroud family and the Rockefeller Foundation and some other funders, and initiated our research center in 1967. Our team, or our centers, sort of have three primary groups. We have a research team, which is the bulk of our 50 staff, give or take, that swells up in the summer with postdocs and interns. So there's a little variation there, but there are 6 science groups at Stroud: entomology, ecosystem ecology, biogeochemistry, fish, microbiology, and fluvial geomorphology. So there's a number of science teams with PhDs and technician staff. The Watershed restoration team, which I manage, is focused on primarily implementation, mostly in agriculture, probably 75 or 80% in agriculture, with some work in suburban and urban systems. And we work very tightly integrated with our research team. It's a great opportunity. It also challenges us every day. All the assumptions we make get questioned regularly by our science team. So we have a pretty robust back and forth. And then we try to very intentionally be spreading the information that we learn through our education network. That's our peers in academia and professional world, as well as watershed groups and kids, sort of all ages. So we have a broad education team that goes through about 8,000 kids per year currently. Just to give you a little insight into some of the kind of work that's going on, there's currently some research that's wrapping up looking at the temperature limitations in aquatic insects. For a long time, folks assumed that these aquatic communities were governed by temperature primarily because temperature governed dissolved oxygen. And I think there's a growing understanding that there's a lot of metabolic processes for our macroinvertebrates that are separate from the oxygen question that have an impact. We do research all across the globe in collaboration with a host of other academic institutions. In addition to the work in Costa Rica, we have some work going on in Switzerland, Peru, and Bhutan currently. We also do some work that's a little more applied. We do a fair amount of academic research on the ag side as well. Some of that's in conjunction with the large land-grant universities like Penn State, University of Maryland. This particular work is sort of looking at some of the specific distinctions around the opportunities and impacts that come with larger concentrated animal feeding operations. For the last probably 7 or 8 years, we've had an increasing focus on resiliency related questions, looking at flood attenuation, looking at infiltration and impacts on stream base flow, and really the time period where we see those impacts occur. This particular project's in a watershed of about 8 square kilometers, and there's a lag time as you do the work on the landscape. We worked very specifically with a number of individual farmers trying to size implementation and best management practices around their operations, and we're sort of stepping outside the box of some of the USDA practice definitions in this case. We've been doing an increasing amount of work on soil and soil health related issues in our watershed. I'll come back to this work a little later on. But I think this is an area that a lot of people are thinking about from a resiliency standpoint, from carbon storage and infiltration standpoint. And this is a project that's probably of particular interest in the context of our conversation. The Delaware River Watershed Initiative was very specifically teed up by a large funder, the William Penn Foundation, to look at aggregating work in small watersheds, and by small I'll say roughly Huck 14 in size, to really attempt to aggregate work, anticipate and model out outcomes, and then measure those outcomes and see whether we're getting the bang for the buck we think we're getting from our implementation practices. I think there's a long history of sort of celebrating individual projects without really looking at the larger outcomes in the ecosystems. The education program works with a host of partners. We have some projects that are working on open source monitoring and DIY environmental sensing work that's national in scope with our partners. We also have a very local kid-centric program, as I mentioned before, up to about 8,000 students per year coming through the program. And we build some tools for broader use, including those open source data loggers and sensor systems, and an online tool for both modeling and monitoring information called Wiki Watershed that you may be worth taking a look at sometime. So back to the restoration discussion and streams and rivers and how we set priorities. So we know these rivers and streams are fairly complex systems. We understand there's sort of a complex web of interaction that drives these systems, and as we change or alter one piece of it, it ripples through the system. That's particularly case, as we talked about a lot today, from the hydrology standpoint and the impact that can have on our systems. It sort of speaks to the inconvenient truth about our stream and river systems, and that is that they are dynamic. They are not static in place or time. Hydrology and ecosystem functions are changing, and that's problematic for us as we try to live and work and grow food in this landscape, because it would be much more convenient if they were consistent and they stayed in one place and they basically did what we wanted and performed the way we liked. And unfortunately, they've never acted that way. You know, these systems are responding to a host of inputs from the climate, from the landscape, and they adapt as they respond. And that's always been the case. I love this picture. This is a Mississippi River meander belt map of the river's location over time. And it sort of brings home the point that we tend to be concerned about erosion, and often for very good reasons, but erosion is a natural process, and it's been going on certainly over time. Before we were here, monkeying around with things and changing the landscape in new ways. So it is one of the problems for us. How do we understand and have a good sense of where the erosion is problematic? How do we address it? And when is it part of natural process? I wanted to just shout out to the folks in Vermont who have, in the aftermath of Hurricane Lee and Hurricane Irene, which decimated the northeastern United States, have really stepped back to look at how they manage these river corridors and these river systems. And granted, most of Vermont doesn't look like Philadelphia or Baltimore, but they've recognized that the costs they were incurring trying to maintain the positions of these streams and rebuild around them after every flood event, and this was starting to happen every couple of years in Vermont, was leading them to think about giving these systems some space. Maybe we really need to think about managing our river corridors by giving these dynamic systems room to adapt to the landscape and climate stimuli that drive them. So I'd encourage you to take a look at their information if you haven't. It's not a panacea. It's not easy, for sure. They've run into all sorts of the political and policy issues you might imagine, including property rights and how do they drive their management system more in this direction, and have it be within the confines of their regulatory and legal system. But I think it is important. We found that it's important for us as we go about our work to think about this, to think about restoration and rivers and streams, not in terms of projects and best management practices and specific modifications, but to think about it as a process, to think about the ecological processes that drive these systems and that they respond to over time. And that's challenging, right? It's not quite the simple cookbook we wish it was, but it may be the only way to manage them effectively in the bigger picture. This is, some of you may be familiar, this is called Lane's Balance. It's the kind of thing that the technical wonky folks among us may grab a beer and stare at for a couple of hours and think about, what if we did this? What would happen on this scale? What if we did that? it's a really interesting description of how river systems respond to changes in their environment. I will say one of the things that's not on here that we think about more and more are some of the boundary conditions that affect our rivers and streams, particularly the smaller ones, thinking about things like root systems of plants in buffer zones. But I just think this is a really useful tool to think about your system, the modifications you're making in the watershed, what that means to the stream, and how it may respond. The other thing that's challenging as we think about our river systems is the scale at which we're working and thinking. And that is, I think, really understandable because most of us are typically working with a specific reach of stream or a project area or a landowner or a development where we're forced to look at our goals and our outcomes and our resources within a fairly short reach of stream. But that does make us approach our options and solutions very differently than when we're able to step back at a landscape scale and think about how would we approach the watersheds in their entirety. It tends, thinking at a reach scale tends to force us to be more channel focused and riparian zone focused. And it tends to lead us to do things that are perhaps more in the line of Band-Aids rather than getting at the core issues that are driving the symptoms we're concerned about in our watersheds. So this is a graphic that a colleague of mine developed. It just gives me headaches and heartburn, actually. She so nonchalantly put natural watershed up there, and I think about, well, what does that mean to us? Do we even have a way to know what pristine is anymore? You think about in many of our landscapes, we have very foundational changes. We have almost no beavers compared to what we have historically. We've had a tremendous colluvial movement of soil from our hill slopes down into our valley bottoms based on agricultural practices and forestry practices over the last 250 years. We really don't have a great understanding of how Native Americans impacted this landscape. We know they used fire fairly extensively. We know they built structures in streams and rivers for fishing weirs. So it's sort of hard to wrap your head around, well, what was natural? And maybe in some ways it doesn't matter because we know we're living in an altered state. We know we have challenges we're trying to address. The key question may be what are our goals for a restored system? How do we set them? What are our expectations of these systems, and can they be accomplished with the constructs and the resources that we have at our fingertips? We know from an ecological standpoint that we have a lot of work to do, and this. If you look at this national survey, nobody's doing great. Some regions of the country that are a little less populous may look a little better, but basically we've got a lot of streams with a lot of problems, and I think that probably doesn't surprise anyone in this room. So the question then really comes down to why is that? Why are we, in spite of spending hundreds and hundreds of millions of dollars on restoration activities, why aren't we delisting more streams? Why don't we see significant ecological improvements in these systems? And most of the streams that have been delisted have been point source impacts, things that are much more easily defined and solutions applied to than our non-point source problems. Seth Brown reminded me yesterday of a quote that sort of applies here that I really like is, we can't manage what we can't measure. And we have real problems measuring these improvements. And in part, that's because we use a lot of models and then we make a lot of assumptions. In part because real monitoring is expensive. And so we've erred on the side of investing our resources in the implementation activities, which is also, I'm not quibbling with that choice, just noting that there are some downsides while we assess our rivers and streams largely through the biology. So the critters that live there, not even sort of the charismatic megafauna of our streams, the brook trout, but the macroinvertebrates are really one of the primary tools we use to assess our success. So I will attribute the slide to my colleague John Jackson, who built it first. This is something we puzzle over quite a bit, and we've tried to think a lot about, well, why is this? Do we have the wrong prescription? Are we taking actions that aren't the most effective? Are we simply not doing enough of them? That in spite of all the investment, we're just not doing enough work to make the changes we're hoping for. Maybe we've missed something completely. And perhaps when you think about how long we've been living and working and growing food in these watersheds, the lag time is just longer than is convenient for us, and that some of these practices are just going to take more time to make the improvements we hope to see. So one of the things we think about first is the models we use. We've become pretty model centric. I think some of that has been driven by the large estuaries, the work in the Chesapeake Bay model, the work modeling for the Gulf of Mexico. And this is, I'm not at all critiquing the effort or the work that's gone in, because those models have become incredibly valuable. But they have some limitations, as do the models that we use more locally. The GWLFE model that is used in Pennsylvania and a number of other states for developing local TMDLs. A lot of these models run on some of the same sets of assumptions and the same sets of nutrient sediment reduction efficiencies based on the same body of research. But they tend to be focused, and I think this does stem from the estuarine drivers, on nitrogen, phosphorus, and sediment. And that's had some ramifications, and it's worked fairly well in the estuarine situations, I think we have to acknowledge. But there are very, very few unique circumstances in our local rivers and streams outside of the estuary where nitrogen is a limiting factor, and becomes a real pollutant of concern. It's just phosphorus tends to be the limiting factor in our freshwater systems. And interestingly, most of our phosphorus load is tied directly to sediment. There's some, I'm not sure, this is something I'm not sure about Arkansas and how this looks out there. We have some areas of intense agriculture and long history of manure application where we've got phosphorus levels in our soil high enough to be in solution in storm events, but that's not that common. So sediment really becomes a critical piece of how these models work and the assumptions we make. And then it gets sort of interesting because we know some things our models don't do well. Our models are typically calibrated to longer term climate data and rainfall events. And when you think about a model that might be internalizing a 30-year climate record for rainfall, and you compare that average to the last 5 years, we're probably making some underestimates about rainfall intensity and runoff in ways that complicate things. Our models also don't do a great job estimating bank erosion. And that stems from a couple of reasons. A lot of times, some models sort of back into those estimates because they assume the overland erosion models are completely accurate, and then they're calibrated at a certain point, and they basically put all the extra in the box of bank erosion. Some of them that are a little more sophisticated have trouble just because it's much easier to account for active erosion rates than it is for sediment fate. And if you don't know where the sediment is actually going, it becomes really tough to make assumptions about the impact of that sediment in your watershed. There's a big difference if it's fine sediments suspended in the water column and making it down to the estuary, or significant amounts of the sediment are actually being deposited on floodplains in large storm events, or building up point bars. So our models, because it's really complicated and expensive to understand sediment fate, we have some problems building that into our models effectively. We'll note, it's easier to poke holes and sort of critique than it is to solve the problem. And I think that's something people are just starting to struggle with. But those sediment realities do create some direction that can become problematic. This slide is from a partner who used to work at the Center for Watershed Protection, now works for the Army Corps. And he was looking at 5 different sites with pest management practices along a stream and looking at estimates of erosion rates at those sites. So these first 2 columns are different methods that Pennsylvania allows for calculating sediment loss in their MS4 plans. And the 3rd column is an estimate created by looking at 2 digital elevation models. I think in this case, they were 11 years apart. And you can see the variability in both the model estimates and the DEM differencing estimate. So there's just tremendous variability that we make a lot of assumptions about as we move into solutions and restoration activity. And that's led us, frankly, to a lot of projects like this, where we're trying to modify the channel itself. And there's very, very little data as we moved into doing more of this work on the ecological efficacy of this work. There's a lot of work done looking at stability and trying to convey the hydrology in a stable manner, and then making assumptions about erosion from the banks. But it's very intense work. I mean, you're probably familiar with it. We see it down on even 2nd and 3rd order streams sometime, bringing in material, grade controls, sometime as often as every 6 inches, every 6 vertical inches, lateral controls, basically, pinning these watersheds into place, these streams into place in the watershed, in a way that completely eliminates their ability to dynamically respond to change. And we've invested a lot of money. This is one of the more expensive projects I'm familiar with. But we see a lot of projects in the $1 to $2 million per mile range that we have to begin to think about that investment, I think. Additionally, while in some cases, if this is done well and it's stably conveying the hydrology, I think you have to ask the question, is perhaps that's enough. I know, some of the urban and suburban scenarios we work in, I I have real questions about our ability to ever effect enough change to delist those streams. The Clean Water Act is very clear. You can't write them off, which creates challenges because I'm not sure how we would ever delist them. But I think we have to question, first of all, whether we're as good as we'd like to be at the structural stability. And we see failures fairly quickly. This is that same stream, 2 points are beginning to fail and cut around the existing structures. And this is a very reputable firm. The work was done for Department of Transportation. And we haven't had, storms of record or anything like that before we start to see these types of failures. We see it a lot. I know there was a little bit of discussion earlier about the regenerative stormwater conveyances, and I think we're getting better at it. But the overbuilding that it takes to be stable in the increasing storm intensities that we see is very, very expensive. And stormwater tends to bring power with it that we underestimate all too frequently, it seems. Perhaps the more challenging piece of this is that even if we were able to be more certain about their stability and their ability to convey these flows over time, the research that's been being done and continues to come out shows that the ecological uplift isn't there. And this is really problematic. I think we have a lot of questions about it. But there's a larger and larger body of research looking at more and more of these streams and sort of noting that changing the hydraulics and the stability, geomorphic issues is not leading to the ecological uplift. I haven't seen a lot of research specifically about the estimates of pollution load reduction and the realities there. So there may be some differences between how you feel about this from an estuarine standpoint, where exported nitrogen is very important, and how you feel about it from a local stream ecology standpoint, which creates some policy challenges for us, perhaps. I think we have a visual aversion to this sort of circumstance, and perhaps that's not all bad. I think we tend to go to hard structures too quickly. There are ways to address this in a softer fashion that allows for some dynamic stability and recognition that things are going to shift over time without trying to pin things to a particular grade elevation or a lateral position. But we have this assumption based largely on our models that the sediment loads from reaches like this are the source of most of our impairment. And I'm not sure that that's as well thought through as we believe it is. This is an exceptional value wild trout stream. I would not call it pristine. It's been untouched for probably the last 180 years. The 50 years before that were pretty ugly, as this area was completely timbered out for early iron production. But we see these types of erosion phases as streams migrate into the valley wall. And again, we could put a bank pin in here, and it would be really easy to measure that sediment loss. But what we don't do very often is think about, well, where did it go? And this is 200 meters downstream. The forest floor here is about 6 inches above the water level in the stream at this point, and you can find a lot of this sediment. Admittedly, we've not done studies to look at actual volumes and numbers, but it's easy to see how in a lot of cases we forget about where the sediment goes. And that's an understandable challenge. But this stream has awesome structure. And it's typical of, I think we see a scenario in a pasture or along a road, and we may view it a little differently than if it were in, a large block of contiguous forest like this. I'd also note that even outside of a larger, older forest, we see trees doing some pretty tremendous work on stream banks once they get their feet established, and we shouldn't forget the stability that they can provide in that context. So I say all that, acknowledging that I used to do a fair amount of that work, and I was increasingly troubled by it. It's just seeing that the science was not supporting it. And frankly, the logic doesn't either. The idea that we can resolve our watershed problems, from the broad watershed, but then the tiny little piece of the watershed that's the riparian corridor is probably a bit naive. So as we move on and think about number 2 here, not enough intensity. Are we doing enough work to make the changes we're hoping for in our watersheds? And I'm going to step away from sort of the stormwater scenario because I know ag better, and just speak to that. But I think the parallels are pretty strong. In an ag context, we have a lot of problems on a lot of our ag, and I think that's true nationally. We have leachate from manure, silage occasionally. We have a lot of uncontrolled animal access to water and barnyard and animal concentration areas. This happens certainly on both the beef and the dairy side of the world. In the mid-Atlantic, we have a particularly large population of semi-aquatic cows. Cows in streams have become the bucolic postcard for central Pennsylvania, I think. But there's real damage done there if you're the stream. And the irony is, this is not very good for the cows either. This hurts their feet, their udders, their production goes down, but seems to be fairly ubiquitous. So the question is how much can we change? And as we think about making changes in this landscape, 40 years ago, 20 years ago, we would have come onto this farm and somebody had, in this case, it was probably Chesapeake Bay money, and they built a manure storage that you can see there in the center of the screen. And what typically happened was whoever helped the farmer put it in walked away. He had made an improvement. He was happy. The farmer did what he had been asked to do, and so everybody was content. But we've left a lot of work undone on that farm, and we shouldn't be surprised when we don't see significant improvements in our streams. I think we do a much better job today of being a little more comprehensive. We know that you can't leave, much of this undone and not mask the improvements. It's just our streams, too many of them they're not close to a tipping point. We have a lot of work to do before we begin to change things significantly. It's all expensive. The ag sector is always under financial duress. I guess we all are at this point. Our older cities and boroughs are in no better shape financially. So these are real challenges for them to face. A really tricky question that I think we were afraid we knew the answer to, and we're seeing validated as we improve and monitor these landscapes, is that you really have to do almost all the farms, because one or two problem areas can mask your improvements. And I think this reality, this concept extends into the suburban scenario too. If you've got problem areas that are significant, you can mask a lot of improvement in the biology and ecology of your streams. So we're guessing that you look at a watershed like this with 11 farms. We're guessing that we have to see 75 to 80% of them addressed pretty comprehensively to see a measurable ecological uplift. That's measurable. That's not to delist. To get them to a point where they're no longer impaired, we're really not sure because we're not there yet. But we may be there. We certainly haven't had enough time for all the changes to play out. But this has been challenging. We're also looking at this in a suburban context in a couple of places, and I think the same approach holds. It's definitely harder. It's definitely more expensive to make the level of change in a suburban landscape than it is in an ag landscape. But I think that's sort of the ballpark that we're thinking about at this point. So moving to number 3, are we missing something? And this is challenging. As we noted before, our models tend to be focused on nitrogen, phosphorus, and sediment, but there's a lot of other things going on out there. Pesticides are expensive to test for, so we often don't, but they're pretty prevalent. Temperature. Temperature has a tremendous impact in streams, not just because of the dissolved oxygen and on the life cycle of the individual species, but also because as temperature increases, it exacerbates the impact of a lot of the chemistry impacts that we have. We know there's other toxins out there from roads and other uses. It can be really hard to pick them up. Depending on how you sample, you can completely miss the spikes or pulses of some of this work. The impact of road salt is something a lot of states are just beginning to struggle with. The use of road salt has really expanded, and we've seen streams that in the wintertime are running salt levels that are about between the salinity of the estuary and the ocean. So really significant impacts. We know pharmaceuticals go basically right through most of our wastewater treatment plants. So we're putting them in our bodies, we're excreting them, and then they're making it to the stream in ways that we really don't understand yet. And there's always new things, right? Someone mentioned earlier PFAS issues. And I think neonicotinoid seed coatings are another issue where everybody was really certain for years that the neonics were immobile, that they were not going to be making it into our waters and our water supplies. And now we can find them almost everywhere. We also, I think the quote from the Pogo comic strip is appropriate. We've met the enemy and he is us. We all use complex cocktail of chemicals in our life. We've all got a shelf under our, in the garage or under the sink with all the things we use, and those make their way into the environment, particularly where population densities are higher in suburbia and urban settings. The use of these things can have a significant impact. So just to change gears a little bit and think about what else we might be missing. It's a little bit my soapbox, but we think of a lot of things in a project context instead of a landscape context. And, forest buffers are one of the ones we've done a lot of work on how they function here at Stroud. Trees in general, frankly, in the landscape are of tremendous value, particularly along our river corridors. They improve temperature. They improve the light quality, which is important for some of the algae species that are at the core of the food chain. They provide particulate and dissolved organic material into our streams that's important in healthy streams. The downwoody debris in streams, creates habitat variability and important. The trees themselves create important roughness on the floodplain to slow down floodwaters. So trees tend to be really important, and we know how to do this, right? We've gotten pretty good at planting trees and establishing buffers and forests fairly reliably, but we think about it in very small pieces, and I'm not sure I have all the answers to think about it more broad spectrum. But I think figuring out how to go about this at a bigger scale is really important for our watersheds. We know the impact this can have. I think Scott Simon noted yesterday that he was amused by a conversation where we're talking about 35 feet or 50 feet or 100 feet of buffer, and that he would prefer trees on the entire floodplain, and I'm completely with him. It's interesting that we try. This is one place where we try to figure out how little we can do. The other thing I note about buffers is that it's really important to do it, not focus on these just the third, fourth, fifth order streams that people think of as their rivers and recreational waters, but the small waters, the headwaters, are incredibly important, and making them as functional as we can is important. Quick commercial. I think it was Travis yesterday who mentioned the importance of maintenance and keeping these things alive. In our part of the world, if you leave it alone, it grows up an invasive species that will overwhelm everything. So we've done a fair amount of work on maintaining these things, keeping them looking good and healthy for people. We've done a lot of buffer work. This is White Clay Creek, where the Stroud lab is located, so it's incredibly well instrumented, and we have an opportunity to learn. We also have a long-term ecological research study going on here, funded through the National Science Foundation, where we have up in the headwaters, there's old forest that's 100 plus years old. The dotted line in the middle of these slides, this time series, is a place that was reforested. So there's about 30-year-old forest there. And the dotted line around the the bottom of the screen there is a stream that was maintained in meadow. And so you can see that progression over time. This is what they look like in the real world today, with the fiberglass rod there for scale. This is the meadow reach. The banks are eroding. It's pretty dynamic, moving across the floodplain. This is the restoration reach with the forest that's about 25 to 30 years old. And you can see this is probably twice as wide, much more variable habitat, much slower rate of movement on the floodplain. And here's the upper reach, which is almost twice as wide, well, 2 to 3 times as wide, probably on average as the lower reach. Again, the fiberglass pole there for reference. So you can see the difference a forest has on our stream system, and we know that this over this is 2012 to I think 2019. I apologize, I don't have the dates on here. I guess pretty stable in position over time in the forest reach. The meadow reach, on the other hand, is more mobile. You can see it pretty quickly there. Interestingly, the volume of this reach, the volume of the channel hasn't changed, and the floodplain is a grading. So this is a net sink for sediment, even though that's not what any of our models would say about it. but it is moving. It's mobile. And if I had a fence or was trying to keep livestock in there, it would be inconvenient, no doubt about it. But you can see the change that's there just with trees in 25 years. So this is another part of that reforested reach, and this is the transition that took place from the time it was planted. No, this is from the time they started measuring it, which was before it was planted. Basically, you can see the black line is the historic stream cross section, and the red line is the current stream cross section. So the forest has enabled that stream to widen. It is shallower on average, but it is much more diverse in terms of depth. And if you look at those two cross sections and think about storm events, the larger cross section in our forested streams will more readily convey the larger storm events we're seeing. And we're still, to be honest, wrapping our heads around exactly how to think about some of this. But the difference is pretty stark. Another reach, you can see the meadow stream is evolving in that 7-year window, from a riffle or a run in the meadow into one of the meander corners. And you can see the thalweg there on to the right. So just for some comparison, you can see the differences in width in the three reaches, and the differences in depth on average. Another really significant difference is the presence of the large woody debris, which creates variability in habitat in these streams. We have every down log in the riparian corridor tagged and surveyed every year, so we know which is moving and how far. And the reality is, it doesn't move as much as most people were concerned about. I just come back to this picture to note that one of the issues here is the grass, right? That it's not deeply rooted, so it's not going to do much to hang on there, which would be different in a forested or some of the shrubs we use for bioengineering, the dogwoods and the willows, which might root that in. I think the other point is, the problem we see, if this is a problem, is a hydrology problem that we need to resolve upstream. That trying to solve it here in this reach is a bit of a Band-Aid, and often an expensive one. And do we invest the money in those sorts of Band-Aids? Do we try to come up with a solution that will give the stream more room to adapt and come to equilibrium? When you look at the cost of some of the projects versus the cost of buying the parcels outright, you really have to give it, I think, more thought than we do, but that's not the way our funding sources are structured. So acknowledge that. And then, even in these high bank situations, we know they look significantly different with trees. I think to get us back up into the landscape, we ask questions about what can we do up on the landscape that will have this difference and allow us to make improvements that aren't in the channel. And on the ag side, the soil health discussion has been dominant lately. There's certainly interest from a climate standpoint in carbon storage. It's fairly easy for folks to use these systems in their ag management systems in a way that's profitable. We know they work. We done the research. Um, you know, this isn't technical, but you can see the difference in runoff from these two systems. It is interesting that in these systems where we have the ability to really measure what's coming off the landscape through weirs like this, in every land condition that we're looking at, we see both volume of runoff and volume of sediment runoff being significantly higher than what our models would predict. And that's not, 50% higher. It's 5 to 8 times higher. And maybe that is simply the result of our models not accounting for rainfall intensity effectively. I think the real win for our watersheds here is the infiltration. We see dramatic changes in infiltration. And this doesn't have to be an ag issue solely. We know changes in soil health are possible in suburbia, and we just haven't effectively, I think, disseminated those solutions or convinced people to embark upon them. But that infiltration goes directly to, in many cases, to the base flow, which is critical to our stream systems in the summertime. So just thinking about this in the urban context, I mean, you're probably all familiar with these types of hydrographs and the changes that urbanization creates in our hydrographs and for our stream systems. When these urban systems really shorten and strengthen the connection between the way we live our lives and our rivers and streams. I think, it's simple to see for people. It is interesting that whether, both of these images, Bryn Mawr is right outside of Philadelphia. There's still a lot of green in our suburban systems. And that brings me back to the point that that Brendan and Andy just made, actually, which is maybe we really need to think about managing the green space we have more effectively. How do we go about? I mean, we have a predilection for maintained turf grass, I think, that we need to struggle with. But we know there are opportunities to better manage the open spaces we have. And then, how do we get into broad implementation of the green infrastructure, which a lot of our speakers know better than I. And I won't spend too much time there because I think folks have done a really good job about it. But these bioretention practices, they all take space, which is the challenge, right? In the urban or suburban setting, how do we make the land available? How do we find the money to retrofit our older practices? Can we do things like adding biochar to make them more effective at addressing some of the chemistry questions? And what is the treatment train and the breadth of implementation we can do in these settings that will get us to our goals, which I think is both a space and a financial challenge, right? Last thing I just want to mention is the time issue. We don't know what the lag time on some of these changes is, and we're trying to learn. We're monitoring. There's a lot of variables, as you might imagine. We're changing a lot of components of the system, and I think that's good. But they all respond differently, and we know some of these things take time to respond. The short version of this is, we know we can see these reductions. The interesting thing is the nitrogen in this experiment rose for the 6 year. It increased for 6 years after the practices were put in place before it started to tail off. So we have expectations that are perhaps going to challenge us with the outcomes we'd like to see. We also know you have to monitor these systems over time, and you can't rely too much on 1 year or 2 year or 3 year data. If you look at these two streams, which reflect different levels of implementation, but just look at the data points on the macroinvertebrate scores in the first couple of years, and the different impression you might have if you tried to fit that line based on 3 or 4 years of data. So it is expensive, and we recognize that, but the long-term monitoring is important. And unfortunately, long-term monitoring sometimes shows us some new challenges. While we've seen streams generally improve, we've seen them be fairly flat in the last couple of years, and we're not sure why. So it does come back to how we measure our success, and do we do it with monitoring? Do we do it with models? And how do we meet the expectations we have for these watersheds? So I will stop there, and I think we have some time for some questions.
Thanks, Matt. Any quick questions? We're running short on time. Anything from the audience on Matt's presentations? Well, I think a couple takeaways for me. One is, you mentioned a lot of these projects fail in 18 months. You mentioned that they're very expensive. And so I think a key question that I came away with is, how do we get to scale on a lot of this? I mean, and what practices are we going to implement to get to that scale? Because we can't afford all of those more expensive $5 million per mile to restore, and it's a lot cheaper an ounce of prevention is worth a pound of cure, as somebody said yesterday. So I think, let's keep that in mind as we move forward and try to address that. Matt, I really want to thank you for this presentation. It presented a more sobering perspective on it, which was enlightening to me because I was all gung-ho before lunch. Brought it back to reality, and really appreciate your time and participating virtually. Thanks so much.
Thank you for having me.